functions. Okay? So things that we have to know, and this is some of the words on your assignment sheet, not even all of them, but it's some of them. But I'm going to use these words throughout the lesson. I just want to preview them here so that you can think about what you already know about that word. And then when you hear me use it, you can refer back and make little notes in this section for that word. Just because this chapter is going to be heavy vocabulary, because the way we communicate about these things use certain terminology that we need to get used to. Okay? Then anything that doesn't get filled in, you have your textbook, you have the internet as resources to then go and fill them in more formally if you're a little bit confused. Does that make sense? Okay. So we're looking for monomial and polynomial, which are both names of certain types of expressions or functions. We have degree that we're going to look at, turning points, and end behavior. So we want to pay attention to what those things mean as we're working through this. Okay. All right. So on your paper, you have 6 graphs. So your graphs look like this. Okay. My formatting is a little messed up here, but you see them at the bottom of the front side right below the vocabulary. So what you're going to do is you're going to split up the work. You guys have 5 minutes, and in the 5 minutes, I want you to get 3 sketches of those graphs. Now, sketches. Do I want you to be perfect in your redrawing of the graph? No. Okay? Sketch. I just want the shape and the general location of the graph. Does that make sense? So you're going to use your graphing calculator. You're going to put these in, and you're going to make a quick sketch of what the graph looks like. What I want you to pay attention to is what type of thing you're graphing. And these have been classified, given a certain equation, they've classified them by their degree, which was one of the vocab words that we talked about, okay? Both in a number, and they've named it based on that degree. So this function right here, f of x equals 2, it's called a constant function, and its degree is 0. Linear function, f of x equals 3 over 2x minus 3. Its degree is 1. It's called linear. X squared plus 2x minus 3 has a degree of 2, and it's called quadratic. Does anybody think that they understand what degree means from prior knowledge or from seeing the way that these equations are written on your paper? Nope. Elizabeth? Good. So basically, as we go up a degree, notice that we're getting a term with a higher exponent in the function. Okay? So this had no x in the function. Its degree was 0. This had an x to the first power. Its degree was 1. This had an x to the second power. Its degree was 2. Now, this function itself actually has 3 terms. One is a quadratic term, one is a linear term, and one is a constant term because the term itself contains a certain number of powers of x's. Does that make sense? So each term has its own degree and its own name. But when you look at them together as one function, you pick the highest one to determine the degree, right? So you might hear someone talking about a quadratic and refer to the linear term. They didn't mess up. They're just talking about the 2x and not the x squared at that moment, okay? But the whole polynomial is classified by that power of 2 being the highest power, and they call it a quadratic, all right? So go ahead and get your graphs on here. You guys all have the paper. You have 6 graphs. If you finish before the rest of us, these are the questions I want you to think about as you look at your sketches. What patterns do you see? I didn't really mean to do that, but apparently I do now. In the end behavior of the graphs, what do you think the maximum number of turning points a graph can have? And what do you think is the maximum number of solutions a graph can have? So after you've graphed these things of all different degrees, I want you to pay close attention to how do they behave at the ends of the graph, the end behavior, turning points, how many times do they turn around, and solutions, how many times do they cross the x-axis. That's if you have extra time in our 5 minutes. Okay, your graphs are done. You want to be thinking of those 3 questions. The first graph that we have here, what did it look like when you graphed it? Okay, by straight you guys mean horizontal? Okay. So a horizontal line is a constant graph, okay? Not as interesting to talk about end behavior. They would say that the end behavior is constant, right? It doesn't go up, it doesn't go down. It's just constant on both ends, okay? All right, what about this line? Okay, so it's diagonal. It has a positive slope, right? All right, so what would you say is the end behavior on this end, okay, this arrow? How is it going to behave? It's going to do what? Keep on going towards what? Negative till it reaches forever, which is infinity. And so we would say your book uses down and up as end behavior, but in pre-calc and in pre-calc honors, you're going to see more references to infinity and negative infinity. So we're going to build that connection now. So this end behavior on this side of the graph is that the graph goes forever downwards, or in other words, it heads towards negative infinity. We just use a negative with the infinity to imply that it's going down towards the negative numbers instead of up towards the positive numbers. What would be the end behavior on the right side of the graph? Good. Infinity. Okay. All right, now, for our quadratic, okay, well, and let me address this. How many turning points does this graph have? 0. No turning points, right? It doesn't turn around. It continues, okay? Quadratic has how many turning points? 1 turning point, okay, at its vertex, or what we referred to previously as its minimum also if it's concave up. What is the end behavior on the left side? Up towards infinity. And on the right side? Towards infinity. Okay? How many solutions does the quadratic have? 2. Does it have to have 2, any quadratic? No. Could have none, it could have 1, but the most it could have is 2. What's the maximum number of turning points it's going to have? 1, because if it turns around again, it will no longer be shaped like a parabola, which is how a quadratic behaves, right? No. So it has a different name. So x to the third is considered a cubic function, okay? So notice this cubic function has a cubic term, a linear term, and a constant term. So you can refer to the degree of each term. The overall polynomial has a degree of 3, therefore it's called a cubic, okay, if we name it by its degree. So when you guys graphed the cubic, it's not going to be super accurate, but it looks something like this, right? So end behavior over here on the left, down, negative infinity, and on the right, up, or towards infinity. How many turning points? 2. How many solutions? 3. Do you think that every cubic has to have 3? No. What if we shifted, because we've talked about translations a little bit, right? What if we shifted this entire graph upward? It could have 2, it could have 1, okay, or downward, but it can't have 0. Why can't it have 0? Yeah, because of the different end behaviors here, okay? Its domain is everywhere, and so is its range, right? Okay. All right, our quartic, and some people in second period were concerned about our quartic. It kind of went like this, right? Kind of looked like a parabola with a kink in it or something, right? Okay. So how many turning points did this graph have? 1. Do you think a quartic could have more than 1 turning point? What do you think is the maximum number of turning points it could have? Good. The degree minus 1 is the pattern we're seeing, which would be 3. Okay. Could turn around. Now the end behavior over here is up. And on the other side of the graph, also up. Right? All right. And then you guys graphed a quintic function. Okay. Sorry that my formatting. After that, we don't care. We call it like polynomial of degree 6. Polynomial of degree 7. They don't keep getting fancy names. Okay. When you graphed your quintic function, did a bunch of stuff, right? Yeah. Okay. How many solutions did this graph have? 5. Okay. Did it have to have 5? No. But it could have 5. Could it have more than 5? No. Why not? Good. It could only have, okay, so turning points, let's go to turning points now. It has 4 turning points, and we just talked about the pattern we're seeing with turning points. 4 is the maximum number of turning points it can have, right? But to cross the x-axis again, I would have to take it and turn it to get it to cross again, right? So then it would exceed the number of maximum turning points it could have, so it would have to be a whole different function. Okay? Now, end behavior over here, it's going down, and over here, it's going up. Okay, so somebody tell me patterns between different types of functions based on end behavior. Let's talk about end behavior first. Predictions you would make. If it's this kind of polynomial function, I predict this kind of end behavior. Molly. Mm-hmm. Good. So look at all your graphs that had even numbered degrees. So your quartic and your quadratic. Their end behavior was both up. Now, can we turn that quadratic so that the end behavior is both down? Could we ever turn the quadratic so that one end is up and one end is down? No. So they don't have to both be up, but they both have to be the same. Okay? What about for our odd degrees? Taryn? Good, opposite directions. And so what we're seeing here is they start down and they end up. Look at your cubic and your quintic and your linear function. They start down, they end up. Okay, Marlon? The most solutions, yes, because it could have infinitely many. Good. So he said if you're a constant, you have the possibility. It's funny because it has, if it's one specific function that's horizontal, it's going to have the most solutions, infinitely many, every number on the number line. But if it's any of the other horizontal lines that exist, it would actually have no solution. So it's very interesting. So our cubic and our quintic, downward negative infinity behavior here, upward positive infinity behavior here. Do you think it could ever go the other way? What do you think would cause it to flip over and start upward and end downward? A negative sign. Good. Our transformations, we saw that with our quadratics, right? Plop a negative in front of it instead of like this, it just flips over. Okay? So the same kind of idea. All right, so a couple of things. Looking at the polynomial structure algebraically, okay, kind of not as much fun as looking at it graphically. So we're going to look at both. So first here, to write the polynomial in standard form, what do you guys think it means to write something in standard form? Good. Largest exponent to the least. Think back to your quadratic. Standard form was ax squared plus bx plus c, right? But here there just might be more power. So I'm going to start with negative 6x to the third, the cubic term, because that's the highest degree I have. Then I'll use my quadratic term, then my linear term, and then my constant. And if it was missing a linear term, then it's missing a linear term, and I go straight from the quadratic term to the constant term. The second part says to name this or label it or classify it. All of those things might mean the same thing based on its degree. So first, what is its degree? As a whole, 3. So each term has its own degree, but as a whole, since 3 is the highest, the degree of this polynomial is 3, and therefore it would be named a cubic. Part C says to name it based on the number of terms it has. So a polynomial is basically anything of this structure where the terms can have coefficients, variables, and exponents on them. The exponents need to be positive integer exponents, or it's not a polynomial. Okay? But for example, this would be a polynomial by itself. Okay? What would we call it if it just had one term and wasn't being added or subtracted with anything else? Monomial. Good. Okay? And if it was like this, binomial, okay? If it was like this, trinomial, and if it's like the one we're looking at here, no, we actually just call it polynomial again. I know. So just like with degrees, we give it names up to degree 5, it gets that quintic, and then after that we say polynomial of degree 6, polynomial of degree 7. We name it special things when we're talking about monomials, binomials, trinomials, but after that we just call them all polynomials, and if you wanted somebody to know specifically how many terms it had, you would just say a polynomial with 4 terms. Really not that exciting. No special name. I'm sure there is a way. Just if you read a math textbook, they're just not going to refer to it using that way. It's just not a way that they generally tend to classify them. But I'm sure if you go back to like Greek, Latin roots, you'll find many ways of classifying these things. All right. Looking at this function, part A, okay? Do you believe the degree of this polynomial, they don't have the equation here, but if the equation was here, would the degree of the equation be even or odd? Even. How do we know that? Good, because they both go up. Okay, so same end behavior, even. What about the graph in part B? Even. Okay. And in part C? Odd. How many real zeros does the graph have in part A? 3. Okay? Well, 1, 2, and this one does touch. So it has 3. Okay? We'll say here, here, and here. Okay? So what do you think is the minimum degree this function could be? It has to at least be 4th power because it's even, but we see 3 roots, and we'll talk about why that would happen here. How about here? Okay, there aren't any real solutions. But based on the shape, what would you think is the minimum degree the function has to be? 4. And since we don't have any zeros, what information are we basing that on? Turning points. We see 3 turning points, right? So we're thinking it at least has to be of degree 4. We might be right, we might be wrong, but we at least have a realm in which we can understand it exists. Okay, here it's odd. How many solutions? 2. Okay, what's the least degree that this could be? A cubic, okay, of degree 3. All right, so we kind of understand this relationship of all those things together. Okay, the second thing, to estimate the turning points of the graph, I think we're actually going to skip this for a minute. You guys can do this. Do you understand what a turning point is now? Okay, so you understand the turning point is here, and you could say, well, that's approximately 0.5, 2.5. And you can name all the turning points. Okay? Yes. So you can name all the turning points. Is that okay? Okay. We did a good enough job earlier. Here's where it gets a little bit interesting. Increasing and decreasing. Highlight all the turning points on your graph. The best way to think of this is, let's say you like reading a book from left to right. So here's Miss Dahl, she's walking, and all of a sudden she's going to walk along the path of the graph, okay, from left to right. That's how you're determining increasing versus decreasing, okay? Consider her distance, okay, from the ground. Say the ground's way down below the graph, okay? So here she gets to our graph. She's walking along the graph from left to right. So as she's walking along this portion of the graph, would the height at which she's at be increasing or decreasing as she moves on? Decreasing. But then you hit the turning point, hence the name turning point, right? It's changing how the function is behaving. So we turn around, and now she's walking on this portion. Increasing. And then here, decreasing. And then here, increasing. I'm going to put some arrows on the ends of these, and please do that to yours as well. So I kind of color-coded them. The decreasing parts were in green, and the increasing parts were in red. And now how to say what's increasing and what's decreasing. So we were decreasing from here forever, right, to the left, until we got to here, okay? So along the x-axis, every value that way is going to be along the graph while the graph is decreasing, okay, until we hit this point right here that's at this x value, say negative 2.5, right? So we are decreasing from negative infinity, because forever to the left, up until we hit the point negative 2.5. Okay? Then we'll argue later about whether at negative 2.5 we're increasing, decreasing, whatever. So for right now, we'll just leave the parentheses like this. Okay? If you put a solid bracket, it means you include that point. So right now I'm saying I'm not. Then we are increasing from negative 2.5 until, I don't know, let's just call it 0.5. Okay? Am I using x or y values to list my increasing and decreasing intervals here? X values. Okay, where along the x value I'm listing? So I said from negative infinity until you got to here, the graph was decreasing. Then from there until you got to here, which was where the next turning point lined up with, you were increasing. There's another decreasing interval on my graph from 0.5 until 3. And then my graph increases again from 3 until infinity, because it never stops increasing. Okay? So there's a verbal way to explain this. There's a way to say the graph is increasing from here to here. But I'm going to get us used to writing it like this. One, it's a lot shorter than explaining it, and you know that mathematicians like notation for everything, right? And two, it's the same notation you're going to see later on. So my goal is to get you as prepped as possible, and if a little thing like this is going to make your life easier later on, right? You see it and you don't have to learn it, then it's better that we're doing it now. Okay? So your homework tonight is all going to be classifying polynomials, stating their degree or naming them, or looking at graphs, identifying how many turning points, solutions, or areas of increasing and decreasing value. So do we feel like we could do that? Yeah? Okay. So homework number 1. Okay. From